段老师在吗？
要稍等一下，我这里那个需要开一下权限。
好的。好的。
现在可以看到了哈。
可以看到了。
好的。大家好，主持人好。My name is Duan Qingling. I'm from Shenzhen Institute of Advanced Technology. My paper number is 22, and my paper title is Three-Dimensional Force Sensor Based on Deep Learning. And my presentation is divided into three parts. First is background, second is method, and the method part is divided into experiment platform. Second is data acquisition. The last is deep learning, and the finally part is experimental results. A flexible sensor is the development trait of sensors in the future. For example, in the tactile sensors such as artificial skin, robot skin, flexible touch screen, and so on. In the tactile sensors, we focus on the force sensors, which used for measuring three-dimensional forces. The previous work, such as traditional soft tactile sensors, these sensors detect the force singular through the change of capacitor resistance and other electric sensors, but they have the problem that nominal pressure interface with shear force measurements. And another sensor is shear force, which is establish the mapping relationship between the labeled point displacement and the 3D forces through a finite element analysis. But this method is simplified a lot, which has a big gap with the actual situation. And the motivation of this paper is that tactile sensors applied to robots are challenging in decoupling 3D forces due to the inability to develop adaptive modules for complex software materials. And the contribution of these papers are as follows. First, a soft 3D force sensor is designed in this paper. Second, the proposed force sensors has a small shape, high decoupling accuracy, and high flexibility, which is suitable for various operations of robot figure types. Figure 1 shows our fusion-based tactile sensors, and the A shows the sensor structure, and the B shows the figure B shows the sensor phototype. As we can see from the figure A, the flexible probe is the center part of the force sensors. The top is covered with a black silicon layer, and then is the colored patterns, which are made of the combination of a number of small colored silicon squares. Next, the bottom is a transparent silicon, and a camera is placed at the bottom of the sensor, which is to capture the silicon deformation. And as we can see, small color squares in the pattern layer were moved to different degrees according to the direction and the size of the force we apply to the sensor. As we can see, the size of the fabricated sensor is small as a button lid. Next is the experimental platform. The experimental system includes mechanical arm, torque sensor, net sources, and our made soft force sensor and the camera. The mechanical arm, which is an industrial robot. We use the UR5, which is used as force application equipment, and its end is equipped with a torque sensor, and in addition, pressure head is installed at the end of the torque sensor, which acts at the soft probe surface. And the torque sensor, we use the commercially available tactile sensor, which is used to record the force applied by the mechanical arm. And the next is the camera. The camera we used is an industrial camera, and the camera is placed at the bottom of the sensor, which is used to capture the deformation pattern. And which is this is the deformation images we captured. Next is the data acquisition process. The fabricated sensor is fixed to the optical platform. Before each experiment, the robotic arms and is moved to the top of the sensor, serving as the start point. The data acquisition process is to reach a given 8 dips to form different normal forces. Under each dip, it will move to 1,000 different positions to form a different shear force. Back to starting point after each shear force is applied. The data acquisition program was realized to control the robot manipulator to move to the specific position, automatically obtain the camera image, and at the same time record the three-dimensional force information. Next, I will show you some original images we have captured. As we can see, under different normal forces, we can get different images, deformation images. Next, I will show you the differential RGB images, which is gated by the pictures under force matters the pictures without force. We can see which is under normal forces. Next, I will show you some shear images we have got. This picture is under no force. This is just under normal force. This is under shear force. This is the differential actual RGB images. This is under normal force. This is under shear force. This is no force. Just the normal force, shear force, normal force, shear force. Now, next, I will show you the deep learning method we have used. This is the input of our deep learning modules, which is differential RGB images. And we match the image to the label. The label is the 3D force once by once, and then we divided them into train dataset and a test dataset. And this is our network structure. And by training the neural network with a large amount of data, the weight parameters of the neural network are determined. Deep learning starts with the training of neural network modules. After we got a trained neural network, we could test our data. We could test our data, and we put our test data as the input into a trained neural network, and then we can get the false information. And the next, I will show you some of our experimental results. This is our soft sensor Mayer force real-time display. Next is one of a force control demo use our soft sensor. We can see underwater the both sides can come close. Underwater it can come close. We take off our bottom, it can automatically 松开. If we didn't use any sensors, it will go full. It will go full again. That's all. Thank you. Hello.
好的，各位老师有要提问的问题吗？没有的话就请黄思阳老师。